So in the last class there was a small technical interruption because of which we could not resume the class once again. Okay, so in the last class we started discussing about the electromagnetic theory, why electromagnetic theory is very important, right? We have also discussed about the weightage in electronics and communications. We have also discussed about the weightage in electrical. Okay, so we have realized that this is a very basic subject. Okay, even it will help us to understand other subjects clearly. We have also discussed about the contents of this particular subject, both for electronics and communications and electrical. Okay, and then we have started discussing with the very first chapter, which is basics of electromagnetic theory. Basics of electromagnetic theory, where we have started with vectors. We have learned what is a vector, magnitude of the vector, direction of the vector, right? So what is a dot product, what is cross product, addition, subtraction of vectors, and we have discussed about the position vector, right? So now we are going to start with discussion of the distance vector. So the learning objectives of today's class is that we will complete the distance vector and we will move into the coordinate systems, right? So that is the focus for today's class, right? So what is distance vector? We have understood what is a position vector. So position vector is something where we try to vectorize a particular point, okay? We try to assign a particular vector to a particular point in space. How do we do that? We just combine that particular point in space with that of the origin in the direction of that particular point to which you wanted to have a position vector. For example, if there is a point called as P, which is designated as x, y, z. Now, if you wanted to have a position vector for this point, so we will combine it with the origin. We will combine it with the origin. So when you do that, then we call this particular vector as a position vector for this particular point called as P. So which is given by as OP bar, which is equal to xi plus yj plus zk. And similarly, we use the concept of distance vector, very important. We often use this particular concept of distance vector. So let us have two points called as P and Q. Let us have 2 points called as P and Q. Now I wanted to have the distance between these two and specifically a distance vector. Specifically a distance vector. So if I wanted to have the distance between P and Q, I wanted to have a vector for it, which is what we are calling as a distinct vector, which is what we are calling as PQ bar, which is what we call as a PQ bar, moving from P to the Q, moving from P to Q, which can be given by what? It can be given by OQ bar minus OP bar. OQ bar minus OP bar. What is OQ bar? OQ bar is the position vector of Q. OQ bar is the position vector of Q. Let us say this is nothing but OQ bar, the position vector for Q, and let us say there is another vector called as OP bar, which is a position vector for P. Then PQ bar, moving from P to Q, is given by PQ bar, which is equal to the of OQ bar minus OP bar. OQ bar minus OP bar. So let this particular point be x1, y1, z1, and let this particular point Q be x2, y2, z2. Now OQ bar minus OP bar is given by what? x2, y2, z2 minus x1, y1, z1. Okay? x2, y2, z2 minus x1, y1, z1, which is nothing but x2 minus x1 in the x direction plus y2 minus y1 in the y direction plus z2 minus z1 and of course in the z direction. So this is what we are calling as a distance vector PQ bar. This is what we are calling as a distance vector PQ bar. And if you want the magnitude of it, the magnitude of this particular PQ bar is given by under root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So this is what we are calling as a distance. This is what we are calling as a distance, and PQ bar is nothing but the distance vector. PQ bar is nothing but the distance vector. So if I'm having 2 points, let us say 1, 2, 3 is my point, and there is a second point called as 0, minus 3, 4. So how can I write the distance vector? The distance vector directed from this particular point 1, 2, 3 to the point 0, minus 3, 4 is given by 0, minus 3, 4 minus 1, 2, 3, which is equal to minus I bar, because this is minus 1. So minus 1 in the I direction, x direction, minus 3 minus 2 is minus 5 in the j direction, y direction, and 4 minus 3 is 1. So 1 unit in the k direction. So this is nothing but the distance vector that we are having over here between the top 1, 2, 3 to the top 0, minus 3, 4. So how we often remember it is that when you are having a particular vector which is moving from a point called as 1, 2, 3 to the point called as 0, minus 3, 4, it is moving from this point to this point. So I can call this particular point as a destination, right? I can call this particular point as a destination. And this point, the other point that we are having, is the origination point. So we can call it as a source. Okay? This is where I've started and this is where I've ended. So I'm calling here it as source and here I'm calling it as a destination. So whenever we are forming a vector called as a distance vector, we always write it as destination minus source. We always write it as destination minus source, which is given by what? 0, minus 3, 4 minus 1, 2, 3, which is equal to minus 1 I, minus 3 minus 2 minus 5 j, 4 minus 3, which is 1 k. Please let me know if you are having any doubt regarding the distance vector, how to form the distance vector. And this knowledge will help us a lot in finding out the electric field and magnetic field in the later classes. So I can see the response. Frame of reference. Very good, Banu. To locate any particular point in space. Right? So to locate any particular point in space, we do require a coordinate system. And as far as electromagnetic theory is concerned, what we actually do is that we try to find electric field intensity or electric flux density or magnetic field intensity or magnetic flux density at some point. Right? We find the electric field intensity or magnetic field intensity at some particular point. So if you don't have a coordinate system, then how can we find the electric field or magnetic field at a particular point? So we do require the coordinate system which helps us to find out the different fields in a best possible manner. And from childhood onwards, we have focused a lot on one coordinate system, which is the Cartesian coordinate system, where we write or express any particular point in terms of x, y and z, right? We express any particular point in terms of x, y and z, yes or no? Correct? But sometimes what happens is that this particular coordinate system, Cartesian coordinate system, it is even though more user friendly, but sometimes to compute the values of electric field or magnetic field, it becomes difficult or cumbersome to use the Cartesian coordinate system. So what we do in that case is that we select an appropriate coordinate system which suits our requirement. For example, if I have a line and this line is going to have a charge on it, let us consider that this line is going to have a charge on it. Now, if I wanted to find out an electric field at a particular point called as P, so what I can do is either express this particular express this particular line and also the particular point that I'm having in terms of the Cartesian coordinate system, and then try to find out the electric field at this particular point. This is the approach, right? We try to express our line charge that we are having, and also we try to express the point P which is in our space, and then we try to find out the electric field intensity. Now what I say is that here, instead of using the Cartesian coordinate system, I will be using something called as a cylindrical coordinate system. I will be considering this as a source, and I know when there is a source, the electric field will go uniformly in all directions. The electric field will go uniformly in all directions. For example, this is my line charge, so the electric field is going to go uniformly in all directions, like this, right? Just like the way we have seen that if there is a charge, So the electric field is going to go in each and every direction, which we are calling as a divergence. In the same way, if you are having the line charge, then the electric field is going to go in different possible directions like this. So what I can do is that instead of considering the Cartesian, I will be considering something called as a cylindrical coordinate system. Cylindrical coordinate system, considering that this particular point is on my cylinder. Considering that this particular point is on my cylinder, and this approach will help us to find out the electric field in an easier manner when compared to that of simply using the Cartesian coordinate system. And same with that of if I'm having a spherical charge, then again if I wanted to find out the electric field, let us say at this particular point called as Q, once again I can try to express this particular source in terms of the Cartesian coordinate systems and this particular point Q also in terms of the Cartesian coordinate system, and then try to find out the electric field intensity. But instead of doing that, what I can better do is that try to express the system that I'm having in terms of the spherical coordinate system. I'll be using the spherical coordinate system because I'll try to consider that this particular point is there on my sphere. I'll consider that this particular point is there on my sphere, and what I can do is that I will express it in terms of the spherical coordinate system, and thereby I'll try to find out the electric field in the spherical coordinate system. This proves to be easy. So the point here is that even though we are very comfortable using the Cartesian coordinate system, many a times it is not suggestible to use only the Cartesian coordinate system, because if you only use that, it will become more and more cumbersome. So what we will be doing is that we will be using the best possible coordinate system which suits that particular problem. So majorly what we are going to discuss here is that we will be of course discussing about the Cartesian coordinate system, which we are of course well aware of, and then we will be going into the other coordinate system which we are going to call as a cylindrical coordinate system, and the third one is the spherical coordinate system. So three coordinate systems we are going to have: 1 Cartesian, 2 cylindrical, and 3 spherical coordinate system. These are the three coordinate systems that we are going to learn in this particular class. So when we talk about the coordinate system, the coordinate systems that we are going to use are actually going to serve two very important criteria which are very much required in this subject. One is the orthogonality, and the second one is right-handedness. Orthogonality and second one is right-handedness. Let us try to understand this from our favorite coordinate system, which is the Cartesian coordinate system. Right? See, let us say that I am having a point P which is expressed in terms of x, y, z. Let me consider that the coordinate system is expressed in terms of x, y, z. Now you see, I will be selecting this as x and this as y, and the other one which is perpendicular, because I cannot represent this on the board, I will be drawing it like this, indicating that it is just a projection of the third dimension on this 2 dimension. Okay, so there are three things that we have. One is x, the other is y, and the third one is something called as z, which is coming outside the board. Now you see, this is what we are calling as x-axis, and this is what we are calling as y-axis, and this is what we are calling as z-axis. Now, what is the x direction? What is the direction of x? The direction of x that we consider is the direction in which the x increases maximum. X increases the maximum, which is nothing but the x-axis itself. So in the same way, this is going to be the y direction, and this is going to be the z direction. Now you see, we consider that the x direction, if it is represented by ax cap, y direction if it is represented by ay cap, and z direction if it is represented by az cap. Now don't you think these three unit vectors that I'm having to represent my coordinate system, any point in space, the unit vectors that I'm having to represent any particular point in space, don't you think these three directions are orthogonal to each other? These three directions that we are having are going to be orthogonal to each other. Okay, so here the orthogonality of a particular coordinate system, the orthogonality of a particular coordinate system is very, very important for us to express any particular point in space. To express any particular point in space. So that is nothing but the orthogonality. That is nothing but the orthogonality. Point number one. Point number two is regarding the right-handedness of the coordinate system. Please understand that this is my x direction, this is my y direction, and this is my z direction. Now, can I represent this as y and this as x and still call this as z? Is it okay for you that for my comfort I am writing here as y and here as x and this as z? Okay, so if you have a habit of doing this, you will slowly understand that you will be doing more and more mistakes. You will be understanding that you will do more and more mistakes. Okay, you might say that, sir, my process is correct, but the answer I got is wrong. It is because you have not selected a proper coordinate system. You have not selected a proper coordinate system. So it's very, very important that this should be x, and after x there should be y, and after y there should be z. So x, then comes y, and then comes z, and then again after z comes again x, after x comes y, and so on. So in which direction are we moving? If I am considering here, so if I am considering here as x, 90 degrees to x I am having y, 90 degrees to y I am having z, right? If I move 90 degrees from x, I will go to y. If I go 90 degrees from y, I will go to z. If I again give a 90 degrees to z, I will once again come back to x and then y. This is what we are calling as the right-handedness of a coordinate system. This is what we are calling as a right-handedness of a particular coordinate system. That you can move x, from there you can move to y, and from there you can move to z, and from there you go to x, and from there you go to y. Okay, so this is what we are calling as the right-handedness of a particular coordinate system. Okay, so there is a question from Shika that can't we go clockwise? No, because we have a particular coordinate system, or any particular angle that we are designing, we consider the angle by default to be in the anti-clockwise direction. We consider it to be an anti-clockwise direction. So if you wanted to consider, because of any reason, if you wanted to consider this as x, this as y and this as x, then it means that if you move from x to y, then basically the other coordinate has to go inside. Here see, if this is x and this is y, from x to y, and then comes the third dimensional which is in z, which are mutually perpendicular to each other. But if I want to consider this as x, this as y, then the third coordinate has to move inside the board. The positive direction of the third coordinate has to move inside the board. Okay, but the way we have selected is that always like this. The way we have selected is that x, then y, and then z. Okay, x, then y, and then z. Is that clear? I can't use this. X, then y, then z. This is my left hand and this is my right hand. From x, you go to y, and from there you go to the z. From x you go to y, and from there you go to the z. Okay, you cannot use your left hand. You cannot go from x, then y, then z. This is not possible. Okay, so the right-handedness of a particular coordinate system has to prevail. So these two criteria are very, very important for the three coordinate systems that we are going to discuss. One is orthogonality, meaning that whatever unit vectors that we have considered for different axes, they have to be mutually perpendicular to each other. The second thing is that the right-handedness of a coordinate system has to prevail. So now let us see the coordinate systems one by one. So first we will be discussing about the Cartesian coordinate system. We will be discussing about Cartesian coordinate system. And second one we are going to discuss is a cylindrical coordinate system. The third one we are going to discuss is the spherical coordinate system. Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. So you can see that the student responds that there is some lag. So I am considering my point. The point that I am going to consider P, let me consider X, Y, Z. So if I project this particular point on the x-axis, the distance covered here is nothing but the x distance. The distance covered here is nothing but the x distance. If I project this particular point on the y-axis, the distance covered is nothing but the y distance. And the same. Okay, actually this particular point is not on the board. This particular point can be on the board, of course, but it can be at any point in space. Okay, but if this particular point comes out, and stands here, it means that it is also going to cover the z distance. So if I'm projecting this point onto the z-axis, if I'm projecting this particular point onto the z-axis, the distance covered along the z, which is what I'm drawing as the z distance, which is what I'm showing as a z distance. So x distance is very clear. If I'm having a point here, the amount of distance covered on the x is what we are calling the x distance. The amount of distance covered on y is what we are calling as y distance. The amount of distance covered on z is what we are calling as a z distance. Okay, so this is nothing but the Cartesian coordinate system we are considering. Now let us draw the unit vectors. We already know the unit vectors. Ax cap, Ay cap, and Az cap. So the direction in which the x component increases maximum is nothing but the x direction. The direction in which y component increases maximum is nothing but the y direction. The direction in which the z component increases maximum is what we call as the z direction. So we are considering the three unit vectors x, y, and z. Okay. See, in some textbooks the x component is mentioned as I. In some textbooks it is mentioned as Ax cap. In some textbooks it is mentioned as x cap. All these three mean the same. And similarly the usage of y or Ay cap or y cap, it means the unit vector in the y direction, or the usage of k, Az cap or y cap also mean, or z cap also mean the same, which is the unit vector in the z direction. Right. So these three unit vectors are very, very important. You will also see that sometimes in the GATE examination also, sometimes they will be using I cap, sometimes they will be using X cap, and in some of the questions they can also use the X cap. Only thing is that you have to be comfortable with the notations. Okay. So now we talked about the orthogonality. So what is the meaning of orthogonality? Ax dot Ay should be equal to 0, right? When you have two vectors which are orthogonal to each other, what is the dot product? If two vectors are orthogonal to each other, the dot product is going to be equal to that of 0. And similarly, Ay dot Az is also equal to 0. Az dot Ax is also equal to 0. Okay. So this is nothing but the orthogonality. This shows the orthogonality. Now what happens to the orthogonality in the case of the cross product? What happens to the orthogonality in the case of the cross product? We have learned that in the case of the cross product, if you are doing the cross product between two perpendicular vectors, then the result is going to be maximum. Here in this case, it will be equal to the multiplication of magnitude of this is 1, magnitude of this is 1, and the angle is 90 degrees. So sin 90 degrees is 1, And what is the direction? What is the direction? X cross y, you will get z. So you'll be getting the unit vector in the normal direction, which is nothing but z direction. Okay. And similarly, if I move from AY cross AZ, AY cross AZ, then it is going to be the x direction. AZ cross AX, it is going to be the y direction. So the easiest way to remember this is using the right-handedness of the coordinate system. Where we can say from x comes y, from y comes z, from z comes x, from x comes y. So if you write x cross y, it is z. If you write y cross z, it is x. If you write z cross x, it is y. See, we will be doing very small mistakes in the examination, right? This is one of them. Okay, sometimes we write AY cross AX is going to be AZ. AY cross AX is going to be AZ, which is wrong, because if AX cross AY is AZ, AY cross AX is going to be minus AZ. If AX cross AY is AZ, AY cross AX is going to be minus AZ. So we will be doing this sort of mistakes in the examination. So the best thing here is that if you have any confusion regarding the cross product, then you can use this right-handedness. So from x you go to y, from y you go to z, from z you go to x, from x you will go to y. So x cross y you will get z, y cross z you will get x, z cross x you will get y. Okay. Right? So this is nothing but orthogonality, right? Ax dot ay is 0, ax cross ay is not 0, it is going to be maximum, which is 1. Now what if I do the dot product between the parallel vectors? Ax dot ax, the dot product is going to be maximum if it is parallel vectors. So the magnitude of this is 1, the magnitude of here 1, the angle between both of them is 0, so cos 0 is 1, and there is no direction because it's a dot product, scalar product. And same with of ay dot ay, and same with of az dot az. Completely it is going to be equal to that of 1. And if I talk about the cross product between the parallel vectors, we all know that if you do the cross product between the parallel vectors, the result will be equal to the of 0. Because in the case of cross product, we are more concerned about the vectors being perpendicular. At least there should be some angle between them. If you don't have any angle between them, which is nothing but the parallel vectors, in that case the result is going to become equal to the of 0. AY cross AY also yields the same result. Even AZ cross AZ is also going to yield the same result. So the range of x component, can you please tell me what can be the range of x? What are the values that the x can take? The x can take any particular value between minus infinity to infinity. Y can take any value between minus infinity to infinity, and z can also take any value between minus infinity to infinity. This is nothing but the range of the coordinates that we are having. X can move from minus infinity to infinity, y can move from minus infinity to infinity, z can also move from minus infinity to infinity. Now let us talk about something called as differential length. Differential length. So what do we understand by the name differential length? So differential length simply means that the smallest length or infinitesimally small length is what we are calling as differential length. Very good. Okay. And the differential length can also be a vector quantity. Be a vector quantity. Okay. For example, if there are 2 points called as P and Q, if you are moving a distance, a considerable amount of distance, then I can call it as LL. If this particular distance is directed, If this vector is directed, then I can call it as L bar. But if the distance between these 2 points is very, very small, if the distance between these 2 vectors is very, very small, okay, so let me draw this particular vector here, Q here, then in that case, the length will be really small, the length will be very small, which I am going to call it as the differential length, DL bar, differential length called as DL bar. Let me consider that the P point is x comma y comma z and the Q point is x plus dx, y plus dy, z plus dz. So what it means to say here is that when you are moving from the point P to point Q, then you are having a small change in the x direction, you are also having a small change in the y direction, again you are also having a small change in the z direction, right? You are having small changes in the x direction, y direction and z direction respectively. Then PQ bar is given by what? The PQ bar is what we are calling as the differential length, DL bar. Can you please tell me from the concept of the distance vector? When you are moving from the point P to point Q, I can write it as dx in the x direction, dy in the y direction, dz in the z direction. Okay. What is the component of dl in the x direction? What is the component of dl in the x direction? What you simply call is nothing but dx, right? We can also write dl bar in the x direction. So the dot product of dl with of the unit vector of the x direction, because you want the component in the x direction. If you want the component in the y direction, you can use the dot product concept, dl dot ay, it gives you dy. If you want the component of the differential length in the z direction, then it is given by az here, which is dz. So after differential length, we are going to discuss about differential surface. Okay. So to understand the differential surface, let me consider that there is a plane. Let me consider this plane is nothing but the xy plane. This plane is nothing but the xy plane. Now please tell me, what could be the direction of this xy plane? Okay, I am having a plane, let us say that this is some cardboard, okay, which you are placing, and we understand that it is nothing but an xy plane. Now if I ask you what is the direction of this cardboard, then what is the direction can we give to it? Very good. So every time we are talking about the direction of a plane, we always show the normal to it. So for example, if I am having an xy plane, the normal to this plane is nothing but the z direction. So, okay, so every time we are talking about a particular surface, a plane, the direction of that particular plane is the normal to it. So what is the normal? Here in this case, it's going to be the z direction. So if I talk about a YZ plane, then the normal which is perpendicular, the normal to the surface, y, z, x. Okay. So after y comes z and after z comes x. Y, z, x. Okay. Y, z, x. So here the direction of this plane is going to be the x direction. And similarly, if I talk about the zx plane, okay, so after z comes x and after x comes y. Zxy, right? Zxy. Right? Now, because here we are discussing about the differential surface. So what I'm going to do is that I'm going to consider a very small part of this xy plane. I'm going to consider a very small part of the xy plane which is having the change in the x direction, as dx, and it is also having the change in the y direction as dy. The change in the x direction is dx, the change in the y direction is dy. Then the differential surface ds is given by dx dy. The differential surface ds is given by dx dy. Multiplication of dx with of dy. And what is the direction of this one? The direction of this particular plane is nothing but, because it is direction, so I'm going to write it as bar here, and here the direction is going to be in the z direction. The direction here is going to be in the z direction. And similarly, when I talk about this particular plane, the ds bar is given by dy dz, and it is present in which direction? A very small part of it. So if I can call it as dy here, and here if I can call it as dz. So dy dz, and of course the direction of it is in the x direction. The differential surface over here. So I am going to consider two small parts here, the change in z direction and also the change in the x direction. So it is going to become dx dz, and of course it is present in the y direction. Okay, so if I am taking all at once, if I am considering a very small part of it, a little cuboid which is having different phases. So particularly if I am talking about three particular planes, first plane, second plane, third plane, then the differential surface in total will be having three directions. Okay, so here what I am trying to write is nothing but a generalized differential surface vector. Here it will be having three directions. One, if I talk about the x direction, where is the x direction? This is the x direction. So the x direction is going to be dy dz. X direction is going to be dy dz. If I talk about the y direction, it is given by dx dz. Now if I talk about the z direction, it is given by dx dy. Now what I can do here is that if you want the x direction, if you want a component in the x direction, so what you will do? The component in the x direction is given by the dot product of ds with of ax, which is given by dy dz. The component of ds in the y direction is given by dx dz. Okay, so this is something we are taking block by block. Now in total, if you see all the three directions together, then you are having something like this. Now I can take component by component, that what is the component in the x direction, what is the component in the y direction, and of course what is the component in the z direction, which is given by dx dy. Okay, so this is the differential surface. The third one is differential volume dV. Now unlike the differential length can be a scalar quantity. The differential length can also be a vector quantity. A differential surface can be a scalar quantity, and the differential surface can also be a vector quantity. But unlike this, the differential volume that we are having, so here this particular block is covering some particular volume. This particular block of the entire big block that I can have the entire big block that I can have, the small part of it, the very small part of it, if I expand, it might be something like this. So the differential volume that I'm having for this is never going to be a vector quantity. It is always going to be a scalar quantity. It is always going to be a scalar quantity because of the simple reason that there is no other dimension, there is no fourth dimension. See, in the case of a differential surface, what we have done, we have taken the direction to it as the third direction because it is present in the 2 dimension, so the direction is given by the third dimension. Now if I am having a volume, it is present, it is already using its 3 dimensions. Now because I don't have the 4th dimension to represent, I can say that this is going to be a scalar quantity. I can say that this is going to be a scalar quantity because there is no 4th dimension to say that, okay, there are 3 dimensions here. So now what I am going to do is that the direction for this volume is going to be in the direction which is perpendicular to all the 3 dimensions I am having, which is not possible. Therefore, we will always indicate the differential volume as a scalar quantity only. So the differential volume is simply given by the change in x multiplied by the change in y multiplied by the change in z. The differential volume is given by the change in x multiplied by the change in y multiplied by the change in z. Please complete it till here. Right, so how can the area be a scalar quantity? See, if I say that there is no necessity of having a particular vector for a particular surface, can I take the scalar value of it? If I say that there is no necessity of having a particular direction, because direction which is associated with a quantity that we are using. Direction is not something that we are using for each and every quantity. It is depending on that particular quantity which we are using. If you have such a particular quantity, then of course the direction matters. For example, if I say that there is a surface like this, there is a surface like this. Now, but the vector that we are having, the vector field that we are having is something like this. The vector field that we are having is something like this. Now, if I want to know what is the component actually matters, what is the component actually matters, then what is my answer? My surface is something like this. Now what is the direction that is actually going to matter for me is the direction in which there is a surface. Then what I say is that, then here in this particular case, I will be taking ds bar dot whatever be the direction of this particular field that I am having. Whatever be the direction of this particular field that I am having. So here there is a necessity of having a particular direction to the surface because I am calculating something which is actually considering the direction of a particular surface as well as the field here. But if this field is not a direction quantity, then is it required to consider a surface with a vector? If I don't associate any particular direction to this particular quantity, then do you think that I want to have a direction to this surface? Okay, so whether we are going to consider a direction for a particular surface or a length, it all is dependent on the quantity to which we are going to deal. So if you are only talking about the scalar quantities, then the length will not have any direction, and of course the surface is also not going to have any direction. But if the quantity that you are considering itself is a vector quantity, then of course you should have a particular direction to length as well as the surface.